All right, welcome back. So we worked pretty hard in the last couple videos to produce this Taylor polynomial formulation, but we didn't even really get time to hammer out an example. So let's do this. So what we're going to do is we're going to find t2 of x, t3 of x for f of x equals ln x at x equals 1. So by finding t2 and t3, we are necessarily venturing beyond the world of tangent lines to essentially the world of tangent parabolas and tangent cubic functions. Since our considerations are at x equals 1, we're going to have to base our computation at that. We're going to have to be computing derivatives, evaluating at 1, and then dividing by the factorial of the derivative computed in order to cook up our coefficients. Once we cook up our coefficients, we're going to sort of assemble our polynomial appropriately. So in terms of cooking up the coefficients, well, we're going to need derivatives. Excuse me. So derivatives here, what? If f of x is ln x, then its derivative is 1 over x. Taking the derivative of that, you could think of this, what, as like x to the minus 1, right? Which would give you minus x to the minus 2. And if you think of minus x to the minus 2 as your second derivative, then when you take derivative again, you'll get 2 over x to the 3, because you'll get 2x to the minus 3, right? Now, computing the derivatives is a piece of the puzzle, but not the whole puzzle. What do we also then need to do? We need to evaluate those derivatives at a. So the leading term is just f of a, so we'll evaluate f of 1 here, which is just 0. So in fact, there's going to be no leading term in this expression, no worries. What about our next term? The next term would be taking f prime evaluated at our a, which would be 1, and dividing by 1 factorial because we've got 1 prime up there. So let's see, that would be 1 divided by 1, which is 1. F double prime evaluated at 1 will divide by 2 factorial for the 2 primes. And then, right, that's going to be what? Evaluating with our f double prime, we'll have minus 1 over 1 divided by 2, which is just minus 1 over 2. What about the constant number 3 would be f triple prime evaluated at a divided by 3 factorial, or in this case, f triple prime evaluated at 1 divided by 3 factorial. 3 factorial because we have 3 primes in our derivative. And this will be, what? This would be 2 over 1 divided by 3 times 2 times 1, which is, well, the 2's would cancel here, and you just get 1 over 3. In fact, if you look at these values of 1 and minus a half and positive a third, you might guess that the next one would be minus a fourth, and you would be right. But what are these values that are popping out? Well, based upon the fact that what? The nth coefficient was the nth derivative evaluated at a divided by n factorial, each of these numbers that are popping out are just the nth coefficient of our Taylor polynomial. And so here we have our 0th coefficient, here we have our first coefficient, here we have our second coefficient, and here we have our third. So if we want to cook up t2 and t3, well then t2 of x would just be f of a, well that's 0. So I'll write the 0 emphatically for our f of a, but then what next? F prime, well that would be 1 times x minus 1. And then to go out to the degree 2 term, well, that's a minus a half. So I'll take my plus and just write it as a minus. Minus a half x minus 1 squared. So we're just taking the coefficients and throwing them into a polynomial which is centered at x equals 1 because our logic was all centered at x equals 1. T3 of x would be 0 plus 1 times x minus 1. I'm just copying the terms that we had in the previous because T3 just includes one additional term, namely the term 1/3 x minus 1 cubed. And again, if you follow the pattern to compute the next subsequent term, you would have like minus, minus 1/4 x minus 1 to the 4th, and then you could have a degree 4 polynomial, which would express an approximation of the function f of x equals ln x at x equals 1. So if we were sort of simplifying this out, which we could do, this first polynomial, maybe we would just write as like x minus 1 minus 1/2 x minus 1 squared. That'd be simpler because the 0 would drop out. Similarly down here, you could do like x minus 1 minus a half x minus 1 squared plus 1/3 x minus 1 cubed. But you get the idea. So if you would take the time to graph what you get here and what you get there versus your function f of x equals ln x, these two Taylor approximations should look very much like f of x equals ln x near x equals 1. If you're far from x equals 1, who's to say what's going on? Because all of our consideration was based upon evaluations at x equals 1. But near x equals 1, t3 should be better than t2 at approximating the function ln x. And T2 would be better than T1. We weren't asked for T1, but say we were, right? This is just our tangent line. Our tangent line would be 0 plus 1 times x minus 1, which would just be, the 0 would drop off, x minus 1. So a degree 1 approximation is great, but a degree 2 approximation is better. A degree 3 approximation is better still. And that's sort of like the theme when it comes to Taylor polynomials. In principle, you could take d up to whatever degree you wanted. What if you went up to degree 100? Boy, you should get a pretty darn good approximation if that was the case, right? Because you'd have a 100-degree polynomial that would have 100 derivatives worth of agreeants at x equals 0 with your original function. My gosh, those two functions should be very similar near that x equals a of interest. And so, yeah, that's something to think about, and yeah, something to get familiar with. But hey, at least we've got one example under our belt, and that makes me feel a little bit better after having talked so much theory in the previous video.